What if I told you that everything you see, the world around you, the stars above, even the laws of physics as we know them, might not be the full picture? There's a tantalizing possibility lurking at the edges of our understanding, a cosmic secret hidden in plain sight. Picture this: invisible realms, entire universes just beyond our perception, subtly tugging at the fabric of our reality. These aren't the stuff of fantasy or wild speculation. This is the frontier of modern physics, where scientists are piecing together clues that suggest our universe might not be alone. Think about the moments when reality seems to glitch, the unexplained gravitational pulls that defy Newton's laws, the strange quantum behaviors that leave even the brightest minds scratching their heads. What if these aren't just random anomalies? What if they're fingerprints of something far grander? The idea of shadow universes, parallel dimensions existing alongside our own, has moved from the fringes of theoretical physics into serious scientific debate. These hidden realms could be interacting with us in ways so subtle, so elusive, that we've only just begun to detect their whispers. This isn't just about solving cosmic puzzles. It's about rewriting the very definition of reality. Imagine a tapestry woven from countless threads, each representing a universe with its own laws, its own history, its own version of existence. Now imagine those threads occasionally brushing against one another, leaving faint but measurable traces in our world. From the mysterious pull of dark matter to the baffling behavior of particles at the quantum level, the evidence is mounting that we're not alone in the cosmic dark. And if these shadow universes are real, what does that mean for us? Could they hold the key to understanding the deepest mysteries of existence? Today, we're diving into the science behind these hidden dimensions, exploring the theories that challenge everything we thought we knew. We'll unravel the strange phenomena that hint at their presence, and we'll confront the mind-bending implications of a reality far stranger than we ever imagined. By the time we're done, you might find yourself looking at the world and the universe in a whole new light, because if shadow universes are out there, interacting with ours in ways we're only beginning to grasp, then the truth is far more extraordinary than fiction could ever dream up. To grasp the concept of shadow universes, we first need to rethink what we consider real. Our universe is built on familiar forces: gravity, electromagnetism, the particles we can see and measure. But what if there's an entire shadow realm operating just beyond our senses, made of matter that doesn't reflect light, absorb heat, or collide with the atoms in your body? This isn't science fiction. It's a serious scientific hypothesis, one that could explain some of the biggest mysteries in modern physics. Take dark matter, for example. Scientists know it exists because of the way galaxies rotate. Their outer stars move faster than they should based on visible matter alone. Something invisible is exerting gravitational pull, and no one knows what. Now imagine if that something isn't just scattered particles but entire structures, planets, stars, even civilizations made of shadow matter, forever hidden from our telescopes. String theory suggests these parallel realities could exist on higher dimensional membranes, or branes, floating like sheets of paper in an 11-dimensional space. If two branes drifted close enough, their gravitational fields might subtly interact, leaving traces in our universe without ever fully revealing themselves. Then there's the quantum world, where particles seem to communicate instantaneously across vast distances, a phenomenon called entanglement. Could this spooky action at a distance actually be evidence of shadow universes subtly influencing our own? Some theorists propose that entangled particles aren't just linked, they're mirror images of shadow counterparts in another dimension, dancing in perfect, invisible sync. The implications are staggering. If shadow universes exist, they wouldn't just rewrite physics textbooks, they'd force us to question the very nature of reality. Are we alone, or is our cosmos just one thread in an unimaginably vast tapestry of worlds, each forever separated by dimensions we can't cross? Every unexplained cosmic anomaly, every gap in our understanding, might be a clue pointing to these hidden realms. And if we learn to decode their whispers, we could unlock secrets that have eluded us for centuries. String theory paints a picture of reality far stranger than our everyday experience suggests. At its core is the idea that the fundamental building blocks of the universe aren't particles at all, but unimaginably tiny vibrating strings. These strings oscillate in different ways, giving rise to every particle and force we know, from electrons to gravity itself. But here's where things get wild. For the math to work, these strings don't just vibrate in the 3 dimensions we're familiar with, or even the 4 when you include time. They require up to 11 dimensions to make sense of their cosmic dance. So where are these extra dimensions hiding? Some theorists believe they're compactified, or curled up so tightly, at scales 1 billion times smaller than an atom, that we'd never notice them in daily life. Picture a garden hose seen from a distance. It looks like a simple line, but up close, you realize it's a tube with a circular dimension wrapped around it. Our universe might be like that, with hidden dimensions folded into the fabric of space-time. But other dimensions could be vast, stretching far beyond our perception, each potentially hosting its own universe with entirely different laws of physics. This is where brane cosmology comes in. Imagine our universe as a thin membrane, or brane, floating in a higher dimensional space. Nearby, there could be other branes, parallel universes just out of reach. Normally, these branes don't interact, but if they ever brushed against each other, the collision could send shockwaves through both realities. Some scientists speculate that the Big Bang itself might have been the result of such a collision, meaning our entire universe could be the aftermath of 2 shadow worlds briefly touching. These interactions wouldn't just be cosmic, one-time events. If branes drift close enough, their gravitational fields could subtly leak into one another. That might explain why 85% of the matter in our universe is invisible. Dark matter could be ordinary matter from a neighboring brane, tugging on our galaxies from a dimension we can't see. Even stranger, particles in our universe might have shadow counterparts in these parallel realities, entangled in ways that defy classical physics. When an electron in our world changes spin, its shadow twin in another brane could instantly mirror that change, no matter how far apart they are. The implications are dizzying. If shadow universes exist, then every unexplained phenomenon, from dark energy's mysterious push on cosmic expansion to the bizarre behavior of quantum particles, might not be a gap in our knowledge but a clue pointing to realities beyond our own. And if we could detect even the faintest whisper of these hidden dimensions, it would revolutionize our understanding of existence itself. The mystery of galaxies spinning faster than they should has puzzled astronomers for decades. When we look at a spiral galaxy, we can calculate how fast its outer stars should move based on the visible matter stars, gas, dust, but something doesn't add up. Those stars are whipping around at speeds that defy Newton's laws, as if invisible hands are tugging at them from the shadows. Scientists call this missing influence dark matter, but what if the truth is even stranger? What if those unexplained gravitational pulls aren't coming from some exotic particle within our universe, but from an entirely different one? This is where shadow universes enter the picture. If parallel dimensions exist, their matter would be invisible to us, yet still capable of exerting gravity across the dimensional divide. Think of it like 2 ships sailing side by side in thick fog. You might not see the other vessel, but you'd feel its wake gently rocking your boat. In the same way, a shadow universe could be lurking right beside ours, its mass subtly warping the motion of our galaxies without ever revealing itself. The evidence isn't just theoretical. Take the Bullet Cluster, two galaxy clusters that collided in one of the most dramatic cosmic events ever observed. When astronomers mapped the aftermath, they found something bizarre. The visible matter hot gas detected by X-rays had slowed down from the crash like cars in a traffic jam. But the gravitational lensing effect, which reveals where mass is concentrated, showed most of the cluster's weight had sailed right through, untouched. It's as if an invisible, intangible force carried the bulk of the mass. Dark matter could explain this, or it could be the gravitational fingerprint of a shadow universe, its matter passing through ours like a ghost walking through walls. Even stranger are the galaxies that seem to move in sync across vast distances, as if connected by some unseen force. The standard model of cosmology can't explain why distant galaxies align in ways that defy probability. But if shadow universes are woven into the fabric of reality, their gravitational influence might create these cosmic patterns, like hidden marionette strings guiding the dance of the stars. These anomalies force us to ask a radical question. Have we been misreading the cosmos all along? Dark matter is still the leading explanation, but it's never been directly detected despite decades of searching. Could that be because we've been looking in the wrong dimension? The idea that shadow universes might be responsible for these gravitational quirks isn't just science fiction. It's a legitimate hypothesis that could solve multiple cosmic puzzles at once. And if we're right, it would mean the universe is far more crowded and far more mysterious than we ever imagined. Now, let's turn to the quantum realm, where particles defy logic in ways that might also point to hidden dimensions. If gravity's odd behavior hints at shadow universes, quantum mechanics could be shouting it from the rooftops. Quantum entanglement is one of the most baffling phenomena in physics, a pair of particles linked in such perfect harmony that changing one instantly alters the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, a phrase that captures just how unsettling this behavior seems. But what if that spookiness isn't just a quirk of our universe? What if it's a window into something far bigger, a hidden conversation between particles stretched across parallel realities? Consider this: when two entangled particles are separated by light years, measuring one immediately determines the state of its partner. No signal travels between them, no force mediates the change, it just happens, as if space and time don't apply. The standard explanation involves quantum superposition and wave function collapse, but some theorists argue that's only part of the story. Imagine instead that these particles aren't just linked in our universe, but are mirror images of shadow counterparts in another dimension. Their instant connection wouldn't require breaking the speed of light, because in higher dimensional space, they might literally be touching, like two sides of the same coin, separated only by a fold in reality we can't perceive. This idea isn't pure speculation. Certain interpretations of string theory suggest that entangled particles could be in points of strings stretching through extra dimensions, tying our world to another. If true, every quantum interaction might be a tiny ripple echoing between universes. Even more intriguing are experiments where entangled particles seem to remember their connection long after they've been separated. Could that memory actually be a persistent link to a shadow dimension, a thread weaving through the fabric of spacetime itself? The implications ripple outward. If entanglement bridges parallel worlds, then the randomness of quantum mechanics might not be random at all, just the visible side of hidden processes playing out in realms beyond our reach. Suddenly, the uncertainty principle isn't about limits to our knowledge, but about the universe literally being influenced by forces we can't see. And if we could ever harness this connection, the possibilities would dwarf even the wildest sci-fi. Imagine communication that defies distance, computers that solve problems by tapping into parallel realities, or sensors that detect the faintest gravitational whispers from other dimensions. Yet the most profound consequence isn't technological, it's philosophical. If particles in our world are entangled with shadow counterparts, then reality isn't just stranger than we imagined. It's stranger than we can imagine. Every quantum event, from the decay of an atom to the firing of a neuron in your brain, might carry echoes of another universe's history. The line between here and there blurs, suggesting we're not isolated observers but participants in a cosmic dance far grander than we ever dreamed. This is why quantum oddities matter. They're not just puzzles to solve, but clues pointing toward a deeper truth. With every experiment that defies expectation, with every particle that behaves in ways that shouldn't be possible, we're catching fleeting glimpses of a reality much larger than our own. And if shadow universes are the missing piece, then the greatest discoveries in physics and in our understanding of existence may still lie ahead. 95% of the universe is missing, at least from our perspective. The stuff we can see, the stars and galaxies that light up the night sky, make up less than 5% of everything that exists. The rest, dark matter and dark energy, two cosmic mysteries that have stubbornly resisted explanation for decades. But what if these aren't just gaps in our knowledge? What if they're actually clues, hints that our universe is brushing up against something far stranger? Let's start with dark matter. We know it's there because of the way galaxies spin, the way light bends around invisible mass, the way galaxy clusters move. Something we can't see is exerting a gravitational pull, and no known particle fits the bill. Traditional theories suggest undiscovered particles lurking in the void, but there's another possibility. Dark matter isn't from our universe at all. It could be ordinary matter, planets, stars, even entire galaxies, from a shadow dimension bleeding into ours. Picture two sheets of paper hovering millimeters apart. If you dropped a marble onto one, it would create a tiny dent. Now imagine that dent tugging ever so slightly on the other sheet. That's how gravity might leak between universes, pulling on our galaxies without us ever seeing the source. Then there's dark energy, the even more puzzling force accelerating the expansion of the universe. No known physics explains why space itself is stretching faster and faster, but shadow universes might. If parallel branes, those higher dimensional membranes from string theory, are drifting apart, their movement could be tugging our universe outward like an invisible tide. Some models even suggest that dark energy isn't a force at all, but the gravitational echo of another universe's expansion, rippling into ours. The beauty of this idea is how neatly it ties together two of cosmology's biggest problems. Dark matter's gravitational effects align perfectly with theories of hidden dimensions, while dark energy's relentless push mirrors what we'd expect if parallel worlds were subtly warping the fabric of our reality. It's as if the universe is leaving breadcrumbs pointing toward a truth far grander than we've dared to imagine. Of course, the skeptics ask, if shadow universes are tugging on ours, why haven't we detected them directly? The answer might lie in the nature of dimensions themselves. Just as a fish in a pond can't perceive the world above the water, we might be blind to forces operating in higher dimensions. Gravity could be the only signal strong enough to cross the divide, faint whispers in the cosmic static. But here's the real mind bender. If dark matter and dark energy are signs of parallel worlds, then the missing 95% of the universe isn't missing at all. It's just elsewhere, Entire civilizations could rise and fall in shadow dimensions, their existence forever hidden from us, yet their gravity subtly shaping the cosmos we call home. The thought is humbling and thrilling, because if we're right, then every telescope, every particle detector, every experiment probing the unknown isn't just studying our universe. It's listening for echoes of countless others. Imagine the early universe, not as a single explosive moment, but as two cosmic giants brushing past each other in the dark. This is the daring vision of brane cosmology, where our entire universe might be the aftermath of a collision between parallel realities. Picture two sheets of paper drifting through space, each carrying its own stars, galaxies, and laws of physics. If they grazed against each other, the energy released could ignite a new universe in an instant. Some physicists argue this isn't just poetic speculation. It could explain why the Big Bang looks the way it does. Take the cosmic microwave background, that faint afterglow of the universe's birth. When scientists mapped its subtle temperature variations, they found something odd, certain patterns that don't quite fit standard inflation models. One theory, these irregularities are cosmic bruises, the fingerprints of a shadow brain smacking into ours during that primordial moment. It's like finding a dent in a car bumper and realizing it tells the story of a long-forgotten collision. But brane encounters wouldn't just be relics of the past. If parallel universes exist, they might still be nudging ours today. Every so often, a shadow brain could sideswipe our reality, sending shockwaves rippling through space-time. These wouldn't be the violent collisions of sci-fi, more like a whisper of gravitational waves or a flicker of unexplained energy in the depths of space. In 2016, the LIGO Observatory made history by detecting gravitational waves from merging black holes. What if future instruments pick up waves that don't match any known cosmic event? That could be our first direct evidence of a neighboring brane making contact. The hunt for these clues is already underway. Telescopes like the James Webb Space Telescope scan the heavens for anomalies in the cosmic microwave background, while next-generation gravitational wave detectors listen for ripples with no obvious source. Even particle accelerators play a role by smashing atoms at unimaginable speeds. They might recreate conditions similar to brane collisions, offering glimpses into how parallel realities could interact. Here's the thrilling part. If we found proof of a brane collision, it wouldn't just confirm the multiverse. It would rewrite the origin story of everything. The Big Bang might not have been a singular beginning, but one link in an endless chain of cosmic encounters, a universe born from the touch of another. And if collisions can happen once, they could happen again. Somewhere out there, another brane might be drifting toward ours, carrying the seeds of a future reality we can't yet imagine. The search for these cosmic whispers isn't just about solving equations. It's about peering behind the curtain of existence, wondering if the universe we know is just one note in a symphony of hidden worlds. Every unexplained signal, every anomalous ripple, could be a message from beyond our dimensional borders, a reminder that reality is far stranger and far more connected than we ever dared to dream. The discovery of the Higgs boson in 2012 was a landmark moment in physics, finally confirming how particles gain mass by interacting with the invisible Higgs field that permeates the cosmos. But what if this same field holds clues to something far more extraordinary? Some theorists suggest the Higgs could be more than just a cosmic weight giver. It might be a bridge between our universe and hidden dimensions, a messenger whispering secrets from shadow worlds beyond our perception. Consider the strange case of shadow photons, hypothetical particles that could slip between dimensions like light passing through frosted glass. Unlike ordinary photons, these wouldn't interact with our matter or electromagnetic fields. They'd move unseen, undetected except for one tantalizing possibility. If a shadow photon occasionally leaked into our dimension, it might leave subtle fingerprints in particle collisions, tiny energy discrepancies that defy conventional physics. At the Large Hadron Collider, scientists scrutinize these collisions with incredible precision, hunting for anomalies that could signal particles vanishing into or emerging from other realities. The math behind this idea is as elegant as it is mind-bending. In certain versions of string theory, the Higgs field could extend into extra dimensions, vibrating in ways that create resonances between parallel branes. Picture a tuning fork struck in one universe. Its vibrations might subtly hum through the Higgs field, faintly nudging particles in another. These interactions wouldn't require dramatic cosmic collisions. They'd be quiet, quantum-scale handshakes between worlds, hidden in the noise of ordinary particle behavior. So what would proof look like? Imagine the LHC detecting a particle that appears to lose energy without explanation, as if some invisible counterpart in a shadow universe absorbed the difference. Or finding Higgs bosons that decay in statistically impossible ways, suggesting their mass was momentarily altered by forces outside our dimensional plane. Even a single verified anomaly could crack open the door to a new paradigm, one where the laws of physics aren't confined to our universe but are shaped by unseen neighbors. The implications ripple far beyond academia. If shadow particles can cross dimensional boundaries, could information or even energy follow? Futurists speculate about technologies harnessing these leaks, quantum devices that entangle with shadow counterparts, or sensors detecting gravitational ripples from parallel realities. More profoundly, it would mean our universe isn't just one isolated experiment in existence but part of a vast, interconnected multiverse, constantly exchanging whispers through the quantum fabric of reality. Yet the greatest revelation might be philosophical. For centuries, we've assumed the cosmos operates by rules we can observe and measure. But if shadow universes are tweaking those rules from behind the curtain, then true understanding requires more than studying our reality. It demands we listen for the echoes of others. Every unexplained particle behavior, every tiny deviation in expected results, becomes a potential message from the dark, hinting that we're not alone in the cosmic expanse. The Higgs field, once thought to be the final piece of the Standard Model puzzle, might instead be the first clue to a far grander mystery, one that redefines not just physics, but our place in the tapestry of existence. Time slips through our fingers in ways we still don't fully understand. Atomic clocks, the most precise timekeepers ever built, occasionally drift out of sync for no apparent reason. Scientists chalk it up to technical glitches, but what if these tiny discrepancies aren't malfunctions at all? What if they're evidence of time itself flowing differently in neighboring universes? The idea might sound like science fiction, but some physicists take it seriously. If shadow universes exist with their own versions of space-time, their gravitational influence could subtly warp the passage of time in our reality, like a hidden pendulum swinging just out of sight, nudging our clocks forward or backward by fractions of a second. Then there's déjà vu, that eerie feeling of reliving a moment you're certain you've never experienced. Psychology offers explanations involving memory misfires, but what if there's a cosmic twist? Imagine parallel timelines brushing against ours, their events briefly overlapping with our own. That fleeting sense of familiarity might not be a trick of the mind, but a fleeting resonance with another version of reality, a ghostly echo of a life being lived elsewhere. It's a controversial idea, sure, but one that challenges us to rethink the very fabric of time. The implications stretch even further. If time in shadow universes moves at different rates, could entire civilizations rise and fall in what feels like an instant to us? Or could moments we experience as fleeting stretch into epochs elsewhere? The concept shatters our linear view of time, suggesting it might not be a river flowing in one direction but a vast, interconnected web of timelines, each pulsing to its own rhythm. Now consider the role of consciousness in all this. If shadow universes interact with ours, could our minds be picking up on signals from these hidden dimensions? Some theories propose that consciousness isn't just a product of our brains, but a phenomenon that might extend beyond the boundaries of our universe, tapping into a broader cosmic network. Near-death experiences, sudden intuitions, even creative inspiration, could these be glimpses into realities that exist just beyond our perceptual reach? The intersection of time anomalies and consciousness opens a dizzying array of possibilities. If time is more fluid than we thought, and if our minds are more connected to the cosmos than we realized, then the line between perception and reality becomes blurrier than ever. What we dismiss as glitches or imagination might be the universe's way of hinting at a far grander truth, one where time, space, and mind are woven together in ways we're only beginning to fathom. This isn't just about solving puzzles, it's about redefining what it means to exist. Every unexplained moment of déjà vu, every flicker of intuition, every atomic clock that ticks just a little off rhythm, could be a breadcrumb leading us toward a revelation that we're not just observers of reality but participants in a symphony of universes, each playing its own melody, occasionally harmonizing in ways we can barely perceive. The next time you feel that strange sense of familiarity or notice time behaving oddly, remember, you might not be imagining things. You might be sensing the whisper of a shadow universe reaching out across the dimensions. Consciousness might be the most mysterious frontier in science, an invisible force that turns electrical signals into rich experiences, thoughts, and emotions. But what if it's doing something even more extraordinary? What if your mind isn't just processing the world around you, but subtly tuning into realities beyond your own? This isn't mystical speculation. Cutting-edge theories in physics and neuroscience suggest that consciousness could be interacting with higher dimensions, acting as a bridge between our universe and shadow realms we can't yet detect. Think about those moments when you just know something without understanding how, like a gut feeling that saves you from danger or a sudden flash of inspiration that seems to come from nowhere. Science often dismisses these as subconscious pattern recognition, but what if there's more to it? Some researchers propose that intuition might be the brain picking up faint signals from parallel timelines or shadow dimensions where alternate versions of events are unfolding. In a multiverse where every possible outcome exists, your subconscious could be tapping into a broader web of information, like a radio tuning into distant stations. Then there are precognitive dreams, vivid experiences where people glimpse events before they happen. Mainstream science struggles to explain these, but if consciousness extends beyond our three-dimensional reality, it might occasionally brush against futures or alternate realities where those events are already occurring. String theory's higher dimensions could provide the scaffolding for these connections, with the brain acting like an antenna, weakly receiving signals from other brains. Even déjà vu, that eerie sense of reliving a moment, might not be a memory glitch but a fleeting overlap with a parallel version of yourself experiencing the same instant in another universe. This idea blurs the line between physics and philosophy. If consciousness interacts with shadow universes, then perception isn't just about interpreting sensory input, it's about filtering a far vaster reality. Your brain might be like a ship's captain navigating by starlight, unaware that what seems like empty darkness is actually teeming with unseen worlds. The implications ripple into neuroscience too. Could disorders like schizophrenia, where people perceive realities others don't, involve an overactive connection to these hidden dimensions? Or might savant abilities, uncanny skills in math, art, or memory stem from the mind briefly accessing knowledge from a universe with different physical laws. The most profound question isn't just whether consciousness connects to shadow universes, but how. Some theories suggest quantum processes in the brain, like microtubules in neurons, could be sensitive to higher dimensional fluctuations. Others propose that consciousness itself is a fundamental property of the cosmos, woven into the fabric of space-time like gravity. In this view, your thoughts aren't confined to your skull. They're ripples in a multidimensional field, resonating with versions of you in other realities. This isn't just about explaining odd human experiences. It challenges the very definition of reality. If our minds can perceive fragments of parallel worlds, then the universe isn't a fixed stage but a dynamic interplay of countless overlapping realms. Every creative breakthrough, every prophetic dream, every uncanny coincidence might be a whisper from the shadows, hinting that we're part of something far grander than we've ever imagined. And if science one day proves this connection, it won't just rewrite textbooks, it'll redefine what it means to be human. Mathematics has always been the silent architect of reality, sketching blueprints for phenomena long before we observe them. When it comes to shadow universes, the equations of M-theory and quantum gravity paint a picture so compelling, it's hard to dismiss as mere abstraction. Take the Kaluza-Klein theory, which describes how extra dimensions could be compactified, curled up so tightly they evade detection. The math isn't just elegant, it's eerily consistent, suggesting that higher dimensional spaces aren't just possible but necessary for unifying the forces of nature. Then there's the Randall-Sundrum model, a groundbreaking framework that imagines our universe as a brane floating in a five-dimensional bulk. Their equations show how gravity could leak into our world from a neighboring brane, explaining its unusual weakness compared to other forces. What's astonishing isn't just that the numbers work, it's that they solve real-world puzzles like the hierarchy problem in particle physics. Suddenly, shadow universes aren't just speculative fiction, they're mathematical inevitabilities waiting for experimental confirmation. But math alone isn't proof. That's where simulations come in. Supercomputers now model brane collisions, tracing how energy would ripple across dimensions during cosmic encounters. These virtual experiments reveal signatures we might observe, anomalies in the cosmic microwave background, sudden bursts of gravitational waves with no visible source, or even particles that appear to vanish into higher dimensions. The simulations are like training wheels for reality, helping us recognize the fingerprints of shadow worlds if they ever brush against ours. The real test, though, lies in the quantum realm. String theory predicts that particles like gravitons, the hypothetical carriers of gravity, could occasionally tunnel into extra dimensions. If detectors like the Large Hadron Collider spotted a graviton disappearing mid-collision, it wouldn't just confirm extra dimensions, it'd hint at entire universes lurking just beyond our reach. Similarly, anomalies in quantum entanglement, particles reacting to forces with no local cause, might reflect interactions with shadow counterparts in parallel branes. Yet the most tantalizing clues could come from the cosmos itself. Astronomers are refining tools to measure deviations in gravity at galactic scales, where the pull of shadow matter might subtly warp spacetime. Others hunt for mirror stars, celestial objects that emit no light but distort the orbits of visible stars through gravitational tugs. If found, they'd be smoking guns for matter from another dimension. The beauty of these models isn't just their theoretical rigor, it's their audacity. They dare us to imagine a cosmos where every equation is a potential doorway, every anomaly a hidden message. And if the math is right, we're not just decoding the universe, we're deciphering a multiverse, one calculation at a time. Long before telescopes or particle accelerators, our ancestors told stories of worlds beyond sight, realms where spirits wandered, gods battled, and the fabric of reality frayed at the edges. The Norse spoke of Yggdrasil, a cosmic tree whose roots and branches connected 9 distinct worlds. Aboriginal Australians described the Dreamtime, a parallel dimension where creation unfolded. The Maya envisioned Xibalba, an underworld layered beneath our own. These myths span continents and millennia, yet they share a startling common thread: the conviction that our world isn't alone. Modern physics dismisses these tales as folklore, but what if ancient cultures were intuiting truth science is only now uncovering? Take the Dogon people of Mali, whose oral traditions described Sirius's invisible companion star centuries before telescopes revealed Sirius B. Or Hindu texts that speak of cyclical universes collapsing and reborn, a concept eerily similar to modern brain cosmology's colliding dimensions. These aren't just coincidences. They're whispers of a possibility that humanity has always sensed shadow universes, even if we lack the language to describe them. Consider shamanic journeys, where healers claim to traverse hidden realms to retrieve knowledge or cure illness. Neuroscience might call these hallucinations, but what if altered states of consciousness temporarily thin the veil between dimensions? Even Plato's allegory of the cave, where prisoners mistake shadows for reality, reads like a metaphor for beings unaware of higher dimensional truths. The parallels are too consistent to ignore. Across cultures, we find recurring motifs: mirrored worlds, cosmic twins, and invisible forces shaping mortal lives. This isn't about proving myths true. It's about recognizing that human imagination may have been groping toward truths buried in the math of string theory and quantum mechanics. When indigenous elders speak of thin places where spirits cross over, could they be describing dimensional weak spots, locations where brains nearly touch? When alchemists sought to transform matter, were they unconsciously probing the quantum entanglement between our atoms and their shadow counterparts? The beauty of this idea lies in its humility. For all our particle colliders and space telescopes, we might be rediscovering what ancient minds glimpsed through intuition and metaphor. Science demands evidence, but art and myth often precede discovery, sketching possibilities later confirmed by data. If shadow universes exist, they wouldn't just reshape physics, they'd reconnect us with a lineage of wonder, a tradition of storytellers who knew, deep down, that reality was always stranger than it seemed. Their visions remind us that the greatest scientific revolutions often begin as heresy, then legend, then fact. Perhaps the next chapter in that story is already being written, not on cave walls or parchment, but in the equations of theorists daring to ask, what if the old tales were right all along? The cosmos is full of riddles that refuse to fit neatly into our scientific frameworks. Take fast radio bursts, those intense, millisecond-long blasts of energy that flash across the universe without warning. They pack more power than a billion suns, yet vanish before we can pinpoint their origins. Traditional explanations point to colliding neutron stars or evaporating black holes. But what if these cosmic firecrackers aren't coming from our universe at all? Imagine a parallel reality where the laws of physics allow energy to build up in ways we can't fathom. If a shadow universe occasionally brushed against ours, the resulting friction could send shockwaves rippling through space-time, appearing to us as those unexplained bursts. It's like hearing thunder from a storm just over the horizon, visible nowhere, yet unmistakably real. Then there are rogue black holes, cosmic nomads drifting through galaxies without a visible trail. Astronomers have spotted these invisible giants by the way they bend light around them, their sheer mass betraying their presence, but their origins remain a mystery. If they weren't born from collapsed stars in our universe, Where did they come from? One provocative theory suggests they're refugees from higher dimensions, black holes that formed in a shadow brane before leaking into ours through a gravitational tear. Picture a bubble passing through a soap film. It leaves a distortion where it touches, then continues on its way. These wandering behemoths might be doing the same, their paths tracing unseen connections between dimensions. Even more perplexing are the galaxies that spin as if they're missing invisible gears. The standard model predicts their rotation speeds should slow toward the edges, yet many whirl at velocities that defy logic, like a car accelerating downhill without pressing the gas. Dark matter is the usual suspect, but another explanation lurks in the shadows. If parallel universes exert gravitational tugs from beyond our perception, their influence could be giving these galaxies an unseen push. It's not so different from how the moon's gravity moves our oceans, except in this case, the tide is coming from another reality entirely. The deeper we look, the more these anomalies stack up. Cosmic filaments, the massive threads of gas and galaxies stretching across the universe, sometimes align in ways that seem orchestrated, as if guided by an invisible hand. Quantum particles occasionally behave as if they're receiving signals from nowhere, violating our expectations of cause and effect. Even the universe's expansion rate, measured differently across various methods, hints at forces we don't yet understand. Each of these puzzles could have mundane explanations, or they could be the first faint echoes of something far grander. What makes the shadow universe hypothesis so compelling isn't just its audacity, but its economy. Instead of inventing new particles or forces to explain each anomaly, it suggests a single, elegant solution. We're not alone in the cosmic dark. The phenomena we can't explain might not be gaps in our knowledge, but cracks in reality itself, tiny windows letting in light from worlds we're only beginning to imagine. And if that's true, then every unsolved mystery in astrophysics isn't a dead end. It's an invitation to look deeper, to question harder, and to wonder what else is out there just beyond the edge of our perception. Of all the particles in the universe, neutrinos might be the most elusive and the most tantalizing. These ghostly travelers pass through planets like Earth as if they weren't even there, rarely stopping to interact with matter. 1 trillion neutrinos from the sun stream through your body every second, leaving no trace. Their near invisibility isn't just a quirk, it could be the key to unlocking one of physics' greatest mysteries. What if these particles aren't just passing through space, but sliding between dimensions, carrying whispers from shadow universes beyond our own? The idea isn't as far-fetched as it sounds. Neutrinos' extreme reluctance to interact with ordinary matter aligns eerily well with theories suggesting they might straddle multiple dimensions. In some models, the same properties that make neutrinos so hard to detect could arise because they spend part of their existence in higher dimensional spaces, only occasionally dipping into our reality. Picture a fish leaping briefly above the water's surface. Observers below would catch only fleeting glimpses, never seeing the full creature. Neutrinos might be doing something similar, flickering in and out of dimensions we can't perceive. This possibility has turned neutrino detectors into cosmic eavesdropping devices. Take IceCube, the massive observatory buried in Antarctic ice. When a neutrino does very rarely collide with an atom, it creates a faint blue flash called Cherenkov radiation. IceCube's sensors capture these flashes, mapping the particles' paths with precision. But scientists aren't just counting neutrinos. They're hunting for anomalies, energies that don't add up, trajectories that bend in unexpected ways, or events where neutrinos seem to vanish mid-flight. Any of these could hint at interactions with hidden dimensions, like ripples betraying the presence of an unseen stone. The stakes couldn't be higher. If neutrinos are indeed crossing dimensional boundaries, they might carry imprints of shadow universes in their quantum states. A neutrino produced in our sun could, in theory, briefly tunnel into a parallel brane before re-emerging in ours, subtly altered by the journey. Detecting such a change would be like finding a grain of sand from another world lodged in the fabric of our reality, proof that we're not alone in the cosmic dark. Even more intriguing are sterile neutrinos, a hypothetical fourth flavor of these particles that would interact only via gravity, not the other fundamental forces. Some theories suggest sterile neutrinos could be entirely confined to higher dimensions, their gravitational influence subtly warping the behavior of their three known cousins. Experiments like the upcoming Deep Underground Neutrino Experiment DUNE are designed to catch these phantoms in action. If they succeed, it wouldn't just expand the standard model, it would tear open a portal to physics beyond our dimensional horizon. The beauty of neutrinos lies in their duality. They're both ordinary, produced in stars, supernova, even nuclear reactors, and extraordinary, with properties that defy conventional explanation. In their subtlety, they might be the perfect messengers, slipping through the cracks between worlds to deliver news of realms we can't yet imagine. Every anomaly in their behavior, every deviation from expectation, is a potential clue written in a code we're only beginning to crack. And if we're right, these ghostly particles could be our first tangible connection to the vast, hidden multiverse lurking just beyond our grasp. Black holes are nature's ultimate enigmas, regions where gravity becomes so overwhelming that not even light can escape. But what if these cosmic monsters aren't just destructive voids? What if they're bridges, twisting space-time so radically that they stitch together distant corners of the multiverse? The math behind this idea is as breathtaking as it is bizarre. When Einstein's equations predict the formation of a black hole, they also hint at something called an Einstein-Rosen bridge, a tunnel through space-time linking one universe to another. These hypothetical structures, better known as wormholes, might not just be science fiction. If shadow universes exist, black holes could be the backdoors connecting them. Picture a black hole's event horizon, the point of no return where gravity's grip becomes irreversible. According to classical physics, anything crossing this boundary is lost forever, crushed into oblivion. But quantum mechanics tells a different story. Information, it insists, can never truly disappear. This paradox has led some theorists to propose that what vanishes into a black hole in our universe might re-emerge elsewhere, not as scrambled debris, but as a coherent signal in a parallel reality. It's like dropping a letter into a mailbox and having it delivered not just to another address, but to another world entirely. The mechanics of this cosmic transfer are even stranger. Inside a black hole, space-time curves infinitely, creating what physicists call a singularity. At this point, the laws of physics as we know them break down. But if that singularity connects to another universe, the infalling matter and energy might not just vanish. They could undergo a transformation, emerging in a shadow realm with its own laws of physics. Some models suggest these connections wouldn't be one-way trips. Just as matter might exit into another universe, energy or information from that universe could bleed into ours, leaving faint imprints in the radiation around black holes. The evidence is still circumstantial but tantalizing. Take Hawking radiation, the faint glow predicted to emanate from black holes as quantum fluctuations near the event horizon. Occasionally, this radiation carries odd anomalies, subtle deviations from what theory predicts. Could these irregularities be echoes of interactions with shadow universes? Or consider the mysterious firewall paradox, where physicists debate whether the event horizon should be a placid boundary or a searing wall of energy. If black holes are gateways, the firewall might not be a barrier at all, but a turbulent interface between dimensions, flickering with cross-dimensional static. The implications are staggering. If even a fraction of the universe's black holes act as portals, then the cosmos is peppered with hidden doorways, each a potential passage to realities where the constants of nature, the shapes of galaxies, even the arrow of time might be utterly alien. Civilizations in shadow universes could be studying their own black holes, wondering if they lead somewhere, never suspecting that somewhere might be us. Of course, skeptics argue that traversable wormholes would require exotic matter with negative energy, something we've never observed. But here's the twist: dark energy, the mysterious force accelerating the universe's expansion, behaves in ways that eerily mimic theoretical negative energy. If the two are connected, the universe might already be supplying the very ingredient needed to prop open these cosmic gateways. This isn't just about rewriting physics textbooks. If black holes are conduits to shadow universes, then the universe isn't a lonely expanse, it's a bustling crossroads, a nexus of hidden connections humming just beneath the surface of reality. Every black hole, from the tiny primordial ones to the supermassive beasts at galactic centers, could be a shimmering thread in a vast, multidimensional web. And if we learn to read their signals, we might finally answer the age-old question: are we alone, or is reality far more crowded and far more connected than we ever dreamed? Imagine the entire universe, every galaxy, planet, and atom, as nothing more than an illusion, a shimmering mirage projected from the edges of reality itself. This is the radical vision of the holographic principle, a theory so mind-bending it challenges our most basic assumptions about existence. According to this idea, the three-dimensional world we experience might be nothing more than a cosmic projection, encoded on a distant two-dimensional surface like a hologram etched onto an unfathomably vast celestial film. Think of how a credit card hologram works, a flat surface that, when tilted, reveals startling depth where none truly exists. Now scale that up to universal proportions. The information that makes up your body, your thoughts, even the stars overhead, could be written on a boundary we can't see or touch, with our perceived reality merely the three-dimensional playback of that data. If this sounds like science fiction, consider the math. Black hole physics suggests the maximum entropy. The information content of any region of space doesn't scale with its volume but with its surface area. It's as if the universe is subtly hinting that the real action happens at the edges, not the bulk. Now here's where shadow universes enter the picture. If our reality is a projection, what's to say there aren't other projections layered atop or alongside ours? Like multiple films being projected onto the same screen, these shadow realms could share the same underlying framework while displaying entirely different worlds. They might even occasionally bleed into one another, creating the cosmic glitches we dismiss as quantum anomalies or dark matter's pull. The holographic principle transforms how we see dimensions themselves. Those extra dimensions string theory predicts they might not be physical directions we could move through, but fundamental layers of information structure. A shadow universe could be another angle in this cosmic projection, a separate rendering from the same underlying code. This would explain why we can't perceive these alternate realities directly. They're not hidden in space but written in a language our three-dimensional perception can't decode. Consider quantum entanglement in this light. When particles instantly influence each other across vast distances, it defies our notions of locality. But if space is an illusion, a projection from a deeper reality where distance has no meaning, then entanglement makes perfect sense. Those particles aren't communicating faster than light, they're fundamentally connected at the level of the source code, where separation is an illusion. Similarly, dark matter's gravitational effects might be shadows cast by information on other parts of the cosmic hologram, invisible to us but still shaping our projected reality. The implications are staggering. If the holographic principle holds, then every law of physics we've discovered might be like figuring out the rules of a video game without ever seeing the computer running it. Shadow universes wouldn't be separate places but alternate renderings from the same cosmic processor, different saves in an unimaginably vast simulation. This doesn't necessarily mean we're living in a computer. The underlying reality could be something beyond our current comprehension, but it suggests that space, time, and matter as we know them are emergent phenomena, not fundamental truth. Perhaps most unsettling is the possibility that consciousness itself plays a role in this cosmic projection. Some interpretations suggest that observation, the act of measurement in quantum physics, might be how the universe renders reality from the underlying data. If true, our minds aren't just experiencing the hologram but actively participating in its creation, entangled with the very fabric of the projection. This would make shadow universes not just alternate realities but alternate perceptions, different ways the cosmic code could be interpreted and experienced. As wild as these ideas seem, they're grounded in serious theoretical work. Physicists are already designing experiments to test the holographic principle, from ultra-precise measurements of quantum foam to searching for pixel-like structures in spacetime itself. Each test is like pressing against the screen of our perceived reality, feeling for the edges of the projection. And if we ever find them, it won't just confirm a theory, it will reveal that the universe is far stranger, far more interconnected, and far more mysterious than we ever dared imagine. The holographic principle doesn't diminish reality. It reveals that what we call real might be just the surface of something infinitely deeper. What if the universe isn't just governed by laws of physics, but by lines of code? The simulation hypothesis, once relegated to late-night dorm room debates, has gained startling traction among scientists and philosophers alike. The idea is simple yet staggering. Our reality might not be the base layer of existence, but an incredibly advanced simulation, running on hardware beyond our comprehension. And if that's true, then shadow universes could be nothing more than parallel processes humming along on the same cosmic supercomputer, separated not by dimensions but by digital partitions. Think of it like a computer running multiple virtual machines, each operating independently, unaware of the others, yet sharing the same underlying resources. Our universe could be one such simulation, with shadow realms operating in adjacent memory spaces. Occasionally, a system glitch, a cosmic buffer overflow, or a quantum rounding error might allow subtle leaks between these simulations. Those leaks could explain the strange phenomena that defy conventional physics: particles that vanish and reappear, gravitational anomalies with no visible source, or even déjà vu moments that feel like memory leaks between instances. The implications grow even wilder when you consider how a simulated multiverse might handle resource allocation. Just as a video game reduces detail for distant objects to save processing power, our universe could be rendering only what we observe, leaving the rest in a low-resolution state. Dark matter, that might be the universe's way of filling in unobserved regions with placeholder data. Quantum superposition, where particles exist in multiple states until measured, could simply be lazy loading, the simulation only committing to a definite state when absolutely necessary. Now imagine what happens when two simulated realities occasionally share computational resources. Entangled particles might be variables linked across simulations for efficiency, explaining their instant connection across vast distances. Fast radio bursts could be cosmic garbage collection temporary spikes as the system reallocates memory. Even black holes might function like compression algorithms, collapsing complex information into singularities to free up processing space. This digital metaphysics doesn't just redefine universes, it redefines consciousness itself. If we're self-aware processes within the simulation, then our minds might be the ultimate glitch, an emergent property the system never intended. Near-death experiences or precognitive dreams could be temporary breaches in firewall protocols, allowing glimpses into other simulation threads. And if shadow universes are running similar processes, their versions of you might be experiencing entirely different realities, all while sharing the same cosmic server. Critics argue this is all untestable speculation, but there are surprising ways to probe the idea. Physicists have proposed looking for pixelation in space-time at the smallest scales, evidence of a resolution limit to reality. Others suggest hunting for mathematical constraints in physical constants, which might reveal optimization choices made by the simulators. Even quantum randomness, long assumed to be truly unpredictable, could show subtle patterns if it's actually pseudorandom number generation. The simulation hypothesis doesn't diminish reality. It reframes it in terms that resonate with our increasingly digital age. Whether you find the idea exhilarating or unsettling, one thing is certain. If shadow universes are running on the same cosmic hardware as ours, then existence is far stranger and far more interconnected than we ever imagined. Every unexplained phenomenon, every cosmic coincidence, becomes a potential debug log entry in the greatest codebase of all, the universe itself. If shadow universes exist alongside ours, teeming with their own stars, planets, and perhaps even life, what might that life look like? Picture a world where gravity is 10 times stronger, where atoms bond differently, or where time flows in unpredictable waves. The creatures evolving in such a realm wouldn't just be alien, they'd be unimaginable, shaped by physics we can barely comprehend. Some might exist as floating, gelatinous masses in high-pressure atmospheres, communicating through pulses of dark energy. Others could be crystalline structures, their thoughts unfolding over centuries in a dimension where entropy works in reverse. The possibilities aren't just endless, they're mind-shattering. Now consider this: if life can emerge in these hidden realms, could it surpass our own intelligence? A civilization evolving in a universe with different fundamental constants might discover technologies that seem like magic to us. Imagine beings who have mastered quantum entanglement to send messages instantaneously across dimensions, or who harness dark energy to fold spacetime like origami. Their science might look indistinguishable from sorcery, their understanding of reality so advanced that our most brilliant theories seem like cave paintings in comparison. This brings us to one of the most provocative questions in modern speculation. Could some of the unexplained phenomena in our world, UFOs, ghostly apparitions, or even mythical creatures, be glimpses of these shadow civilizations? The idea isn't as far-fetched as it sounds. If brains occasionally brush against each other, even briefly, higher dimensional beings might momentarily flicker into our perception, appearing as distortions in the sky or figures that vanish when approached. Some UFO sightings, particularly those where craft defy known aerodynamics or disappear without a trace, fit eerily well with theories of interdimensional visitors. But here's the twist: if shadow universes host life, we might not be the hunters in this cosmic search. We could be the hunted. Advanced civilizations in neighboring dimensions might already be studying us, their sensors tuned to the gravitational ripples or quantum echoes leaking from our brain. Our planet, bathed in radio waves and artificial light, could be as conspicuous to them as a bonfire in the night. The thought is humbling and thrilling. It suggests that the search for extraterrestrial intelligence shouldn't just scan distant stars, but probe the very fabric of reality for cracks where other worlds might peer through. Of course, skeptics argue there's no evidence yet, but absence of proof isn't proof of absence. 100 years ago, the idea of black holes or quantum particles sounded like fantasy. Today, they're textbook science. The same could be true for shadow life. Future detectors sensitive enough to measure the faintest gravitational anomalies or quantum hiccups might one day catch the equivalent of a cosmic hello from across the dimensional divide. Until then, the idea serves a deeper purpose. It stretches our imagination beyond the limits of one universe, one set of physical laws, one evolutionary path. Whether shadow life exists or not, contemplating it reshapes how we see our place in the cosmos. We're no longer just inhabitants of a lonely planet orbiting an ordinary star. We're part of a vast, possibly infinite tapestry of realities, each with its own stories, its own thinkers, its own dreamers gazing back at us through the veil of dimensions, wondering if they're alone too. Quantum tunneling is one of the strangest tricks in nature's playbook, a particle suddenly appearing on the other side of an impenetrable barrier, like a ghost walking through walls. In our everyday world, this makes no sense. If you threw a ball at a mountain, you wouldn't expect it to pop out the other side. But in the quantum realm, particles do this routinely, vanishing from one place and materializing in another without traveling the distance in between. The math explains it as a probability wave slipping through the barrier, but what if there's more to the story? What if these particles aren't just tunneling through space, they're briefly slipping into other dimensions? This idea isn't as outlandish as it sounds. String theory suggests that higher dimensions could be curled up incredibly tiny, far smaller than an atom. At the quantum scale, a particle tunneling might momentarily dip into one of these hidden dimensions, bypassing the obstacle entirely before snapping back into our reality. Think of it like an ant crawling across a folded piece of paper. If it steps into the fold, it can skip part of the journey without breaking any rules. If true, quantum tunneling wouldn't just be a quirk of physics, it'd be a fleeting glimpse into the architecture of the multiverse. Laboratories are already probing these possibilities with mind-bending experiments. Take quantum dots, nanoscale crystals where electrons are trapped in tiny energy wells. Normally, they'd need a big energy boost to escape, but sometimes they just do. If these tunneling events leave even the slightest trace, an extra burst of energy, a tiny delay, it could hint that the electron briefly visited a shadow dimension before returning. Other experiments monitor radioactive decay, where particles like alpha tunnels unpredictably out of atomic nuclei. The timing of these decays is eerily random, but what if the randomness comes from interactions with unseen dimensions, like dice being rolled in a hidden room? The most tantalizing evidence might come from the quantum vacuum itself. Empty space isn't really empty, it's a seething foam of virtual particles popping in and out of existence. Most vanish instantly, but occasionally they stick around just long enough to be detected. Could some of these particles be refugees from shadow universes, momentarily crossing into ours before fading back? Some theorists suggest that the Casimir effect, where two metal plates in a vacuum inexplicably pull toward each other, might be influenced by extra-dimensional particles nudging them from beyond. If these dimensional leaks are real, they'd rewrite our understanding of reality. Every quantum event, from photosynthesis in plants to the firing of neurons in your brain, might involve particles briefly flirting with other universes. The implications ripple outward. Could we one day harness these leaks to communicate across dimensions, to extract energy from shadow realms, or even to detect civilizations in parallel branes by their quantum fingerprints? The experiments are ongoing, the theories evolving, but one thing's certain: if particles are tunneling not just through barriers but through reality itself, then the universe is far stranger and far more connected than we ever imagined. Cosmic strings sound like something ripped from the pages of a science fiction novel, threads of pure energy thinner than an atom yet stretching across the entire universe, carrying the mass of entire stars. But these aren't just theoretical oddities, they're potential scars from the birth of the cosmos, defects in space-time itself left over from the universe's earliest moments. Picture the universe cooling from its fiery infancy, like molten glass solidifying into delicate crystal. Just as imperfections form in cooling glass, cosmic strings could be cracks in the fabric of reality, frozen in time since the first trillionth of a second after the Big Bang. What makes these strings so fascinating isn't just their existence, it's where they might lead. Some theories suggest these filaments don't just wind through our universe but pierce through higher dimensions, stitching multiple realities together like threads through layers of cloth. If true, a cosmic string could be a literal bridge to shadow universes, a hidden freeway connecting worlds we can't otherwise perceive. The gravitational waves rippling along these strings might carry whispers from other dimensions, faint tremors that could one day be detected by observatories like LIGO. Even stranger is what happens when these strings vibrate or intersect. Just as plucking a guitar string creates a musical note, a vibrating cosmic string could generate waves in spacetime itself. Not the gentle undulations of ordinary gravitational waves, but sharp cymbal crash distortions. These events might leave behind bizarre signatures, sudden flashes of gamma rays with no visible source, or galaxies mysteriously split into mirror image halves by a string's passage. In 2020, astronomers spotted a candidate cosmic string in the form of a peculiar double quasar, two identical quasars where only one should exist. Could this be the aftermath of a string slicing through space, creating a gravitational lens so precise it produced a perfect cosmic copy? The most tantalizing possibility is that cosmic strings don't just connect points in our universe but tether multiple realities together. Imagine two shadow universes linked by a string, their gravitational fields subtly intertwining like trees sharing roots underground. Matter from one reality might flow along these filaments into another, explaining anomalies like rogue black holes or dark matter's gravitational tug. Some models even suggest that if a string looped around itself, it could pinch off a pocket of spacetime entirely, birthing a new universe in the process, a literal thread of creation spinning new worlds into existence. Detecting these strings won't be easy, but the hunt is already on. Telescopes scour the skies for strange, linear gravitational lensing effects, starlight bent into perfect lines rather than the usual arcs. Pulsar timing arrays listen for the distinctive twang of a string's gravitational echo disrupting the steady beat of distant neutron stars. Even the cosmic microwave background might hold clues, its temperature variations potentially bearing the imprint of strings that brushed our universe billions of years ago. The beauty of cosmic strings lies in their duality. They're both relics of our universe's violent birth and potential gateways to realities beyond it. If they exist, they're not just curiosities, they're the frayed edges of the cosmic tapestry, hinting at a grander weave where every universe is part of a vast, interconnected whole. And if we ever catch one's shadow, it won't just confirm a theory. It'll reveal that the universe is far more than we see, a place where even the cracks in reality might lead somewhere extraordinary. Astronomers have long assumed the universe expands evenly in all directions, like a balloon inflating, until they noticed something that shattered that assumption. Hundreds of galaxy clusters, each containing thousands of galaxies, are streaming through space at staggering speeds toward the same patch of sky, as if drawn by an unseen force. This bizarre cosmic migration, dubbed dark flow, defies everything we know about the large-scale structure of the universe. According to standard cosmology, matter should distribute randomly after the Big Bang's initial push, with no preferred direction. Yet these clusters move with eerie coordination, like leaves caught in a hidden current. The numbers are staggering. These clusters race at over 2 million miles per hour toward a point near the constellations Centaurus and Vela, faster than should be possible given the known mass in that direction. Some researchers argue it's a statistical fluke or measurement error, but the signal persists across multiple studies. If not a flaw in our data, what could possibly exert such titanic gravitational pull? One radical explanation points beyond our universe's borders. Just as the moon's gravity creates Earth's tides, a neighboring universe, or something even more unfathomable, might be tugging on ours from outside space-time itself. Imagine two soap bubbles floating close together. Though their surfaces never touch, the slight gravitational attraction between them could create ripples. Now scale that up to universes. If a massive shadow realm exists parallel to ours, its gravity might subtly warp the motion of galaxies near the edge of our cosmic bubble. This wouldn't require direct contact, just the faintest whisper of influence across the dimensional divide. The dark flow's direction could literally be pointing toward where this neighboring universe lurks, a cosmic finger tracing the shape of the unseen. Critics counter that such ideas venture too far into speculation, and they're not wrong. Dark flow remains controversial, with some attributing it to uneven radiation pressures from the early universe or relic effects of inflation. But here's what's fascinating. Even if shadow universes aren't the cause, the phenomenon still exposes gaps in our understanding. The universe isn't just expanding, parts of it are sprinting somewhere, and we don't know why. That alone should give us pause. Future telescopes like the European Space Agency's Euclid mission aim to map dark flow with unprecedented precision, hunting for patterns that might reveal its source. If the flow strengthens at certain distances or aligns with anomalies in the cosmic microwave background, it could hint at forces beyond our cosmological models. We might even discover that what we call dark flow is really the universe tilting towards something vast and hidden, a gravitational landmark in a reality far larger than we ever imagined. The most profound lesson of dark flow isn't just about unseen forces. It's a reminder that the cosmos refuses to behave as our textbooks predict. Every time we think we've mapped the edges of reality, the universe reveals another layer, another mystery whispering that we've only begun to explore. Whether the culprit is shadow universes or something even stranger, one thing is clear: the universe is moving, and it might be heading somewhere we can't yet see. The ground beneath our feet feels solid, dependable, but the universe itself might be standing on far shakier foundations. Deep within the quantum fabric of reality lies a terrifying possibility: vacuum decay. Picture the universe's lowest energy state, the so-called true vacuum, lurking like a cosmic landmine. Our current reality might exist in a false vacuum, a precarious high-energy state that could, at any moment, collapse into something far more stable and cataclysmic. If a single quantum fluctuation triggered this transition, a bubble of true vacuum would erupt at light speed, rewriting the laws of physics as it expands. Atoms, stars, even space-time itself would unravel in its wake, leaving behind a sterile void where nothing we recognize could exist. Now imagine this apocalypse isn't just a local disaster, it's a multiversal contagion. If shadow universes share a deeper quantum connection with ours, the collapse of one could send shockwaves through the cosmic web. Like dominoes toppling in the dark, a vacuum decay event in a neighboring brane might propagate through higher dimensions, seeding instability in our own universe. The math is chilling. A single quantum crack in a parallel reality could spiderweb across existence, dooming worlds we never knew existed. The mechanism behind this cosmic contagion isn't pure speculation. In certain brane cosmology models, universes aren't isolated, they're like grapes clustered on a vine, sharing underlying quantum fields. A vacuum collapse in one could perturb those shared fields, nudging neighboring branes toward their own tipping points. Some theories even suggest that dark energy's mysterious acceleration might be an early warning sign. A faint tremor from a distant universe's death throws echoing through the dimensional divide. This isn't just theoretical doom-mongering. In 2018, physicists at Harvard calculated how vacuum decay bubbles might leave gravitational wave imprints detectable by future observatories. These wouldn't be the waves from colliding black holes we've observed, but sharper, stranger signals, cosmic SOS beacons from universes that couldn't save themselves. Even more unsettling are models suggesting that if one bubble can form, others likely already have. Our universe might exist in a sea of decaying realities, their boundaries creeping toward us at light speed, invisible until it's too late. Yet there's a paradoxical beauty to this fragility. If vacuum decay can cross dimensional borders, then the multiverse isn't just a collection of isolated worlds. It's an interconnected ecosystem where each reality's survival depends on the stability of others. The same quantum threads that might allow shadow universes to whisper to ours through entanglement or dark matter could also carry their death knells. In this light, the hunt for gravitational anomalies or vacuum fluctuations isn't just academic. It's cosmic vigilance, an early warning system for existential threats we're only beginning to comprehend. The chilling takeaway: we may never see the danger coming. A shadow universe's collapse could ripple into our reality as a sudden rewrite of physical constants. One moment the stars shine, the next quarks cease to bind and matter dissolves into quantum foam. But this dire scenario also offers an unexpected comfort, proof that we're not alone in the cosmos. Even the end of everything would be a reminder that existence is vaster, stranger, and more intimately connected than we ever dreamed. Time crystals sound like something ripped straight from a science fiction epic, structures that don't just exist in space but pulse rhythmically through time itself, like a heartbeat woven into the fabric of reality. Unlike ordinary crystals with their repeating atomic patterns in 3 dimensions, time crystals break symmetry in the 4th dimension, cycling through states with clockwork precision without any energy input. It's as if they've tapped into the universe's hidden metronome, ticking endlessly in perfect, self-sustaining loops. But here's where it gets even stranger. These exotic phases of matter might not just be curiosities confined to our universe. Some physicists speculate they could stretch across dimensions, threading through the cosmic dark like luminous filaments connecting parallel realities. Imagine a time crystal as a bridge between worlds, not a physical structure you could walk across, but a quantum link resonating in sync across multiple branes. Just as a tuning fork vibrates at a specific frequency, a time crystal's rhythmic oscillations might harmonize with counterparts in shadow universes, creating a subtle, enduring connection. This isn't just poetic speculation. The math suggests that if higher dimensions exist, the periodic structure of time crystals could extend into them, their vibrations echoing where ordinary matter cannot reach. Laboratories have already created primitive time crystals using chains of ions or diamond defects, chilling them near absolute zero to observe their eerie, self-repeating behavior. If these lab-born crystals can mimic the theoretical blueprint, What might nature have forged on cosmic scales? The implications are staggering. If time crystals span dimensions, they could serve as nature's own interdimensional antennas, structures sensitive to fluctuations not just in our universe, but in shadow realms brushing against ours. Picture a scenario where a time crystal in our world subtly alters its rhythm, not because of any local influence, but because its counterpart in a parallel universe has been disturbed. Such a phenomenon wouldn't just hint at hidden dimensions, it would provide a roadmap to them, a way to trace the invisible contours of the multiverse. Even more tantalizing is the possibility of communication. If time crystals in different universes can entangle, locking their rhythms across dimensional divides, they might transmit information in ways that defy classical physics. No need for faster-than-light signals or wormholes. The data could flow through the shared heartbeat of the crystals themselves. Futurists dream of time crystal networks, arrays of these structures tuned to detect, or even broadcast patterns into the cosmic dark, a Morse code tapped out across the multiverse. Of course, skeptics argue that time crystals are too fragile, too small-scale to play such a cosmic role. But consider this, the first synthetic time crystals were created in just the last decade. If humanity can engineer these phenomena in a lab, what might the universe have sculpted over billions of years? Black holes, neutron stars, and other extreme cosmic environments could host time crystals of unimaginable size and stability, their rhythms pulsing across eons and across dimensions. The hunt for these eternal shadows is already underway. Quantum sensors are being refined to detect minuscule temporal symmetries in exotic materials, while astrophysicists scour neutron star data for anomalies that might betray the presence of natural time crystals. Every flicker of regularity in the chaos of the cosmos could be a clue, a whisper from a shadow universe saying, "We're here." And if we ever learn to listen, to truly understand the language of these crystalline echoes, we might discover that time itself is the thread stitching the multiverse together. You've probably had that moment someone mentions a childhood memory, and you're absolutely certain it happened one way only to discover the world insists it didn't. The Berenstain Bears weren't spelled with an E, despite your vivid recollection of Berenstein. Nelson Mandela didn't die in prison in the 1980s, even though you swear you remember news coverage of his funeral. These collective false memories, known as the Mandela Effect, are more than just quirks of human psychology. They might be cracks in reality itself, fleeting glimpses into parallel worlds where history unfolded slightly differently. At first glance, the Mandela Effect seems like a simple case of misremembering. Our brains are imperfect recorders, stitching together fragments of experience with biases and assumptions. But when thousands of people independently recall the same incorrect details down to specific logos, movie lines, or historical events, it raises a tantalizing question. What if these false memories aren't false at all? What if they're accurate recollections of events that did happen, just not in this version of reality? This is where the multiverse theory collides with neuroscience. Imagine infinite parallel timelines branching from every decision, every quantum fluctuation. Most of these universes remain forever out of reach, but what if our consciousness occasionally flickers between them? Like a radio briefly picking up a distant station, your mind might momentarily tune into a timeline where the Monopoly man wore a monocle he didn't, or where "Luke, I am your father" was the actual Star Wars line. It's "No, I am your father." These aren't mistakes, they're echoes of realities where those details were true. The science behind this idea walks a razor's edge between speculation and cutting-edge physics. Quantum mechanics already allows particles to exist in multiple states until observed, a principle called superposition. Some interpretations, like the many worlds hypothesis, take this further, suggesting every quantum possibility spawns a new universe. If consciousness arises from quantum processes in the brain, as some theorists propose, then our awareness might transiently overlap with these alternate worlds, blending their histories with ours. Skeptics argue that cultural reinforcement and suggestion better explain the Mandela Effect. Once someone mentions Berenstain, our brains retroactively adjust the memory. Yet even this doesn't account for the eerie specificity of these shared falsehoods. Why do so many remember the same non-existent Sinbad genie movie from the 1990s? Why do identical, alternate details surface globally, unprompted? Perhaps the truth lies somewhere in the shadows between psychology and physics. Our brains may indeed misremember, but the consistency of these errors could hint at something deeper, a subconscious network tapping into a broader cosmic tapestry. Every Mandela Effect might be a footprint left by a version of you in a neighboring timeline, a phantom imprint whispering that reality is far more fluid than it seems. And if that's the case, the next time someone corrects your memory, you might smile and wonder, or are you the one who's misremembered? Deep beneath the Swiss-French border, in a circular tunnel spanning 17 miles, scientists are smashing particles together at nearly the speed of light, not just to understand our universe, but to potentially break through into others. The Large Hadron Collider at CERN isn't just the world's most powerful microscope. It's a battering ram against the walls of reality itself. When protons collide with enough energy, they don't just shatter into familiar fragments like quarks and electrons. They might momentarily warp space-time so violently that particles vanish into higher dimensions. In 2010, researchers observed fleeting energy discrepancies in certain collisions, as if some of that energy had slipped through an invisible door. Though later attributed to statistical noise, the tantalizing possibility remains. What if the next anomaly isn't a glitch, but a shadow universe waving back? Meanwhile, halfway across the world, another experiment listens for whispers from the dark. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detects ripples in space-time from cataclysmic events like colliding black holes. But in 2020, it picked up something odd, a gravitational wave signal that didn't match any known cosmic phenomenon. Dubbed GW 190,521, the event defied expectations, with some theorists suggesting it could have been a primordial black hole from a parallel brane brushing against ours. Imagine dropping a pebble into a pond and seeing concentric rings suddenly twist into knots. That's the kind of anomaly physicists are hunting for, distortions that shouldn't exist unless space-time itself is fraying at the edges. But the hunt isn't limited to massive machines. On a smaller scale, quantum experiments are probing the fabric of reality with exquisite precision. Take neutron interferometry, where subatomic particles are split into two paths and recombined to test the limits of wave-particle duality. In 2015, a team at the Vienna Institute of Technology noticed neutrons behaving as if they'd briefly interacted with, something. The particles' phase shifts suggested an unseen influence, like a ghostly hand tweaking the experiment from behind the curtain. Could these be fluctuations from a shadow dimension, where alternate versions of the same particles are simultaneously running their own experiments? What ties these efforts together is the pursuit of anomalies, the cosmic breadcrumbs that might lead us beyond the known. At the Gran Sasso Laboratory in Italy, scientists are monitoring ultra-pure crystals for spontaneous flashes of light, a potential sign of dark matter particles interacting with ordinary matter. If dark matter is truly matter from a shadow universe, these detectors are essentially eavesdropping on another dimension's radioactivity. Similarly, quantum entanglement experiments, like those at the University of Geneva, are testing whether particles can remain connected across not just space but higher dimensions. If entangled pairs show correlations that defy local causality, it might imply their partners aren't just far away, but exist in a parallel brane entirely. The stakes couldn't be higher. Every unexplained energy spike, every gravitational wave that doesn't fit the template, every quantum particle that behaves just slightly wrong could be the first hard evidence of a multiverse. And the tools to find it are evolving rapidly. Future gravitational wave detectors like the Einstein telescope will be sensitive enough to catch whispers from the universe's first second, potentially revealing imprints of brane collisions. Next-generation colliders, like the proposed Future Circular Collider, could reach energies where extra dimensions become visible if they exist. Even tabletop quantum experiments are reaching unprecedented precision, turning lab benches into portals for probing the fabric of reality. Yet the greatest challenge isn't technical, it's philosophical. How do you design an experiment to detect something you can't imagine? The history of science is littered with discoveries that defied expectation, from quantum mechanics to dark energy. The shadow universe hunt may require rethinking not just our instruments, but our very definition of evidence. After all, if another dimension is leaking into ours, its signature might not be a clear signal, but a subtle skewing of probabilities, a statistical tilt in the data that says, look closer. Something's here, and when we find it, the discovery won't just rewrite textbooks, it'll redefine what it means to exist in the cosmos. If shadow universes exist alongside ours, teeming with alternate versions of reality, then everything we think we know about free will collapses into a dizzying paradox. Picture a cosmic kaleidoscope where every choice you've ever made or didn't make unfolds simultaneously across infinite dimensions. That latte you skipped this morning. In another universe, it led to a conversation that changed your life. The job you turned down. Elsewhere, it launched a career that reshaped history. Suddenly, the idea of choice feels less like steering a ship and more like flipping through channels, each decision point branching into endless variations of you. This isn't just theoretical. Quantum mechanics already suggests particles exist in superpositions until observed. So why wouldn't consciousness, emerging from those particles, share that fluidity? The chilling implication: your sense of agency might be an illusion, a local phenomenon blind to the symphony of selves you're part of. Now consider identity in this fractured cosmic mirror. If countless versions of you exist across shadow universes, each shaped by slightly different physics, histories, or even laws of logic, what makes you fundamentally you? The memories you cling to, the traits you cherish, could be accidents of your universe's particular configuration. In a realm where gravity is stronger, your bones might be denser. Where time flows erratically, your childhood might span centuries. Some versions could be unrecognizable, a you who never evolved on Earth at all, but as a plasma-based being swirling in a nebula. Yet beneath these divergences, a thread persists, the pattern of your quantum information, echoing across dimensions like a fugue. This suggests identity isn't anchored to biology or even continuity, but to something deeper, an abstract mathematical signature that transcends individual realities. The nature of reality itself unravels under this scrutiny. Our universe's constants, the speed of light, the charge of an electron, feel absolute. But if shadow universes operate by different rules, then these aren't laws so much as local ordinances. What we call reality is just one slice of a vast, mutating hyperverse where logic itself might be fluid. Imagine a dimension where cause and effect reverse, and you remember tomorrow while anticipating yesterday. Or one where entropy runs backward, reassembling shattered vases and extinguishing stars into unborn gas clouds. These aren't just thought experiments, they're plausible configurations in the multiverse landscape, making our version of existence seem provincial, even arbitrary. Yet the most profound shift isn't in physics, it's in meaning. If every possible outcome occurs somewhere, does achievement lose its value? Does regret? The answer lies in recognizing that while alternate selves exist, your experience remains singularly vivid. The branching of worlds doesn't dilute existence. It magnifies its richness like a prism splitting light into hidden colors. Your choices still matter, not because they're unique, but because they're yours, a specific melody in the multiverse's chorus. This perspective doesn't diminish humanity, it elevates it. We're not just inhabitants of a universe, but participants in a grand ontological tapestry, each thread shimmering with its own truth. The shadow realms don't erase our significance, they invite us to redefine it. The moment we confirm the existence of shadow universes, humanity faces an ethical crossroads unlike any before, one that could redefine our future as a species. On one hand, reaching across the dimensional divide might unlock unimaginable knowledge, civilizations that solved problems we haven't encountered, technologies that harness physics beyond our grasp, even answers to existential mysteries like dark energy or consciousness itself. The temptation is overwhelming, but on the other hand, what if making contact triggers consequences we can't foresee? Imagine a scenario where interdimensional communication destabilizes the fragile quantum fields binding our reality, like shouting in a cosmic avalanche zone. The risks aren't just theoretical. In 2008, fears that the Large Hadron Collider might create Earth-swallowing black holes sparked global panic, and that was just about particles in our own universe. Now scale that anxiety to meddling with entire alternate realities. History offers sobering parallels. When European explorers first encountered isolated indigenous societies, the results were often catastrophic disease, cultural erasure, unintended wars. The same could hold true for interdimensional contact, but with stakes magnified to cosmic proportions. A shadow civilization might perceive our signals as hostile, deploying technologies we can't comprehend to neutralize the perceived threat. Or worse, their very existence could rely on physical laws incompatible with ours. A simple handshake across dimensions might unravel local space-time like a pulled thread, collapsing both universes into a vacuum decay cascade. Yet the ethical dilemma cuts both ways. If shadow universes host intelligent life, don't we have a moral obligation to seek them out? The universe's greatest loneliness would be knowing others exist and choosing isolation. Some ethicists argue that withholding contact is akin to refusing to help a drowning swimmer, a violation of the fundamental principle to reduce suffering. Others counter that the precautionary principle must prevail. We'd never forgive ourselves if a single experiment doomed trillions of beings across multiple realities. The debate mirrors humanity's most pivotal moments: nuclear fission, AI development, gene editing, but with an added layer of existential vertigo. At least with atomic bombs, we understood the physics. Here, we'd be operating in realms where our science might be as rudimentary as a caveman's understanding of radio waves. Proposed safeguards, like using neutrinos or quantum entanglement for low-impact signaling, offer no guarantees. Even a harmless laser pointed at the sky could, in theory, intersect with a higher dimensional structure we don't yet perceive, triggering chain reactions in unseen realms. Perhaps the most unsettling question isn't whether we can contact shadow universes, but whether we should be the ones to initiate it. If other civilizations exist, why haven't they reached out already? Their silence might be strategic, a recognition of risks we're too curious or arrogant to acknowledge. Or it could hint at something darker, that in the multiverse's grand Darwinian arena, only civilizations that stay hidden survive. Until we know more, our greatest ethical duty might be humility, to listen rather than shout, to study rather than interfere. The cosmos has kept its secrets for billions of years. A little patience might be the wisest exploration of all. Quantum computers could be the master keys to unlocking the secrets of shadow universes, not by peering through telescopes, but by simulating realities beyond our own. Imagine a machine that doesn't just calculate faster, but operates across multiple quantum states simultaneously, each state representing a different configuration of hidden dimensions. Google's Sycamore processor, which achieved quantum supremacy in 2019, hinted at this potential by solving in minutes what would take classical supercomputers millennia. Now scale that power to model brain-world collisions or higher dimensional particle interactions. These aren't just abstract calculations, they're potential blueprints for where and how to hunt for dimensional leaks in our universe. The real breakthrough may come when quantum AI begins noticing patterns in these simulations that human physicists overlooked, anomalies that point like cosmic arrows toward the hiding places of shadow realms. Meanwhile, gravity sensors are undergoing a revolution so precise they could detect a feather's weight on Pluto. Projects like the Laser Interferometer Space Antenna LISA, set to launch in the 2030s, will float 3 spacecraft in perfect formation, using lasers to measure space-time distortions smaller than an atom's width. But here's the kicker. If a shadow universe's gravity subtly warps our own, these sensors might catch its fingerprint as a periodic ripple in the data, an oscillation that matches no known astrophysical source. Even more tantalizing are proposals for atomic interferometers, which exploit quantum properties of atoms to measure gravitational forces with absurd sensitivity. Picture a cloud of ultra-cold cesium atoms suspended in a vacuum, their quantum waves stretching and compressing in response to forces we can't see. If matter from a parallel universe tugs on them, even faintly, the resulting interference pattern could reveal the presence of an invisible neighbor. Artificial intelligence is already transforming cosmology by sifting through petabytes of telescope data for cosmic oddities. The Vera Rubin Observatory's legacy survey of space and time will generate more astronomical data in one night than all previous telescopes combined, an avalanche no human team could process. Machine learning algorithms, trained to recognize the subtle gravitational lensing patterns of shadow matter or the spectral signatures of higher dimensional particles, might spot what human eyes miss. In 2022, an AI at the University of Heidelberg discovered dozens of new gravitational lenses in old data that astronomers had scanned for years without noticing. Now imagine that same power applied to hunting for cosmic strings, those hypothetical scars from brane collisions, or decoding the quantum noise in particle colliders for evidence of particles tunneling between dimensions. The AI wouldn't just be analyzing data, it'd be learning the hidden language of the multiverse. The most radical tools might come from merging these technologies. Quantum machine learning could enable AIs to think in superpositions, exploring countless hypotheses about shadow universes simultaneously before collapsing into the most probable solution. Gravity-sensing nanodrones swarming through space like cosmic plankton might map the gravitational field of our galaxy with enough detail to reveal the shadows of parallel masses warping space-time from another dimension. Even our humble internet infrastructure could play a role. Some theorists propose that entangled quantum networks might accidentally link to their counterparts in shadow universes, creating detectable correlations across the dimensional divide. What makes this technological frontier so electrifying isn't just the potential for discovery, it's the sheer creativity of the hunt. We're no longer limited to waiting for shadow universes to announce themselves. We're building the tools to interrogate reality itself, demanding answers at scales and energies previously unimaginable. And if even one of these experiments succeeds, the payoff would dwarf every scientific revolution in history. The day we confirm a shadow universe's existence won't just rewrite textbooks, it'll shatter the very framework of human knowledge, revealing that the cosmos is vaster, stranger, and more interconnected than we ever dared dream. Hollywood has painted parallel universes as shimmering portals or glowing doorways, where heroes leap between realities with a single step. But strip away the special effects, and the real science behind shadow universes is far more subtle and infinitely stranger. Take the Marvel multiverse. While Doctor Strange's sling ring portals make for thrilling cinema, real theoretical physics suggests any connection between dimensions would likely be invisible, detectable only through quantum whispers or gravitational ripples. The truth is, if you stumbled into a parallel universe, you might not even realize it at first. Consider the classic trope of mirror universes, where everything is reversed, a staple from Star Trek to Stranger Things. In reality, a shadow universe wouldn't be a perfect reflection of ours. It could have entirely different physical laws. Gravity might repel instead of attract, time could flow backward, or matter might assemble into forms we can't comprehend. The idea of encountering an evil mirror version of yourself is fun fiction, but the genuine article would be far more alien. Imagine a world where atoms don't exist, replaced by entirely different building blocks. No doppelgangers, just an existence utterly unrecognizable. Then there's the speed of light barrier. Sci-fi often ignores it, with ships or signals zipping between dimensions instantly. Yet if shadow universes exist in higher dimensional space, crossing over might not mean traveling at all. Picture two sheets of paper floating side by side. You can't walk from one to the other, but if they briefly touch, particles might transfer without traversing the gap. This aligns with quantum tunneling, where particles vanish and reappear without crossing the space in between. No warp drives required, just the bizarre rules of the quantum realm. But perhaps the biggest myth is the idea of controlling or conquering parallel worlds. Films like Everything Everywhere All at Once suggest we could verse jump at will, harnessing alternate self skills. In reality, even detecting another universe would be a monumental challenge, let alone interacting with it. The energy needed to pry open a stable gateway between dimensions would dwarf anything our technology could muster. Think collapsing stars, not glowing sci-fi gadgets. And if string theory's extra dimensions are as tiny as predicted, entering one might mean shrinking smaller than a quark, a feat beyond any foreseeable engineering. That said, reality has its own brand of magic. While Hollywood's portals are pure fantasy, phenomena like quantum entanglement, where particles influence each other across vast distances, hint at a universe far more interconnected than fiction dares to imagine. The sci-fi trope of alternate timelines isn't entirely off base either. The many worlds interpretation of quantum mechanics suggests every decision spawns new branches of reality. The difference, these branches aren't places you could visit, they're mathematical possibilities, diverging forever beyond our perception. The irony is profound. While movies simplify the multiverse for storytelling, the genuine science is wilder than any script. A real shadow universe wouldn't just have a version of Earth with different history. It might not have planets, stars, or even space as we know it. Its existence would rewrite not just physics but philosophy, forcing us to ask, what does it mean to be real when countless other realities might thrive unseen? The answer, much like the cosmos itself, is still unfolding. Every strange glitch or eerie coincidence doesn't automatically mean shadow universes are knocking on our door. While the idea of hidden dimensions is grounded in serious physics, pop culture often blurs the line between science and science fiction, turning cosmic mysteries into clickbait. Take déjà vu, often romanticized as a glitch in the matrix or a memory leak from a parallel life. Neuroscience offers a simpler explanation, a temporary hiccup in brain processing where familiarity fires before recollection. That's not to say shadow universes couldn't play a role in unexplained phenomena, but jumping to interdimensional conclusions without evidence risks turning a profound scientific inquiry into a modern-day myth. Then there's the persistent myth that shadow universes are just like ours, only slightly different. A world where you made that left turn instead of a right, or where dinosaurs never went extinct. While the multiverse theory does allow for alternate timelines, the reality is far wilder. A true shadow universe might not even have recognizable matter, let alone Earth-like planets. Its physics could be so alien that concepts like left or right wouldn't apply. Imagine a realm where gravity repels, where time loops like a Möbius strip, or where entropy runs backward. These aren't just tweaks to our reality, they're complete reinventions of existence itself. Another common misconception, that shadow universes, if they exist, must be constantly interacting with ours in dramatic ways, portals opening, objects vanishing, or people swapping places. In reality, most theoretical models suggest these interactions would be vanishingly subtle, detectable only through painstaking measurements. The gravitational tug of dark matter, the faintest anomalies in quantum experiments, or the unexplained spin of distant galaxies. These are the breadcrumbs scientists actually follow, not glowing doorways or time-traveling doubles. Even if shadow universes are real, their influence might be as quiet as a whisper in a hurricane, easily drowned out by the noise of everyday physics. Sensational headlines love to claim that experiments like the Large Hadron Collider could open a portal to another dimension, unleashing chaos. But the truth is far less apocalyptic. While particle colliders do probe extreme energies, any interaction with shadow universes, if it happens at all, would likely manifest as a barely detectable statistical blip in data, not a rip in spacetime. The real work of uncovering hidden dimensions is slow, meticulous, and often frustrating. It involves ruling out countless mundane explanations before even considering the extraordinary. Critical thinking is the anchor here. The search for shadow universes isn't about chasing ghosts or confirming conspiracy theories. It's about following the evidence wherever it leads, even if that path ends in a dead end. Scientists don't assume dark matter is shadow matter. They test the idea, discard what doesn't fit, and refine their models. That's the essence of good science, curiosity tempered by skepticism, wonder balanced with rigor. So the next time you hear a wild claim about parallel worlds, ask the hard questions. Is there data to back it up? Could there be simpler explanations? The universe's greatest mysteries deserve more than just exciting stories. They demand our sharpest minds and most disciplined imagination. Because if shadow universes are out there, uncovering them won't happen through fantasy or fear, but through the patient, persistent light of scientific inquiry. The hunt for shadow universes is accelerating with tools that would have seemed like pure science fiction just decades ago. Picture the James Webb Space Telescope, floating 1,000,000 miles from Earth, its golden mirrors capturing whispers of light from the universe's infancy. Beyond studying distant galaxies, its infrared gaze might spot anomalies in the cosmic microwave background, subtle temperature fluctuations that could bear the fingerprints of a neighboring brane brushing against ours in the primordial fireball of the Big Bang. Meanwhile, deep underground in abandoned mines and mountain tunnels, teams are setting up ultra-sensitive detectors like the Deep Underground Neutrino experiment. where liquid argon tanks the size of apartment buildings will track elusive particles that might momentarily dip into higher dimensions before vanishing. These aren't just experiments, they are interstellar fishing nets cast into the quantum void in hopes of snagging something from beyond our dimensional shores. But the real game changer might be gravitational wave astronomy. Future observatories like the Einstein telescope, with its 10-kilometer-long laser arms, won't just listen for collisions of black holes, they'll hunt for the faintest tremors in spacetime that no known cosmic event can explain. Imagine detecting a ripple that doesn't match the signature of any neutron star merger or supernova, but instead carries the harmonic resonance of a higher dimensional object vibrating in ways our universe can't naturally produce. It would be like hearing a note from an instrument that doesn't exist, a cosmic chord played on strings from another reality. Yet for all this technological firepower, the biggest hurdle remains sheer scale. If extra dimensions are compactified, curled up at sizes a billion times smaller than an atom, how do we probe such infinitesimal realms? One radical approach involves quantum gravity sensors that exploit the bizarre behavior of particles at near absolute zero temperatures. When atoms are chilled to quantum states, their wave-like nature becomes sensitive to perturbations smaller than a proton's width. If a higher dimension tugs on these atoms even slightly, their interference patterns could shift in telltale ways, revealing hidden geometries folded into the fabric of space itself. The unanswered questions loom just as large as the tools we're building. Why do we perceive only 3 spatial dimensions if others exist? Are they permanently locked at microscopic scales, or could some be vast, parallel landscapes we simply can't access? Perhaps most perplexing of all, if shadow universes are real, why haven't their inhabitants, assuming they exist, made contact? The silence could imply physical barriers we don't yet understand, or something more unsettling, that crossing the dimensional divide is inherently destructive. A one-way trip that unravels the traveler's fundamental structure. This isn't just about satisfying curiosity. Cracking the code of shadow universes could answer existential riddles that have haunted physics for generations. Dark energy's mysterious push, the unsettling randomness of quantum mechanics, even the arrow of time itself, all might be side effects of realities beyond our own, nudging the edges of our cosmic bubble. Every unexplained phenomenon becomes a potential clue, a breadcrumb leading toward a revolution in understanding. The journey ahead is equal parts exhilarating and humbling. We might confirm shadow universes within our lifetime, or the evidence might remain teasingly out of reach for centuries. But one thing is certain. The search stretches the limits of human ingenuity, demanding we build machines that listen to the faintest echoes of creation while daring to ask questions that redefine reality itself. Whether we find them or not, the pursuit transforms how we see the universe, not as a solitary stage, but as one trembling thread in a vast, shimmering tapestry of worlds. The idea that we might be sharing our universe with unseen neighbors, entire worlds brushing against ours in the cosmic dark, is both exhilarating and profoundly grounding. Think about it, every unexplained gravitational tug, every quantum particle that behaves just a little too strangely, could be a postcard from a reality we've yet to fully comprehend. For centuries, humanity believed we were the center of creation, only to learn the Earth revolved around the Sun, which turned out to be one unremarkable star among billions. Now we stand on the brink of another revolution, one that could reveal our universe as just a single thread in a vast, shimmering tapestry of realities. What makes this search so compelling isn't just the science, but what it says about our place in existence. If shadow universes exist, then the cosmos isn't just vast, it's layered, folded, humming with hidden complexities. The same curiosity that drove us to map the stars and split the atom now pushes us to probe the very fabric of reality, asking questions that once belonged solely to philosophy and myth. Could dark matter be the gravity of stars we'll never see? Are entangled particles secretly holding hands across dimensions? Every experiment, from neutrino detectors to quantum simulators, is a vote of confidence in the universe's willingness to reveal its secrets. Yet for all our tools and theories, humility remains essential. The universe has a way of outstripping our wildest imaginations. 100 years ago, black holes were mathematical oddities. Today, we've photographed one. The lesson: today's science fiction often becomes tomorrow's textbook. Whether shadow universes are confirmed next year or centuries from now, the pursuit itself reshapes how we see reality. It's not just about finding answers, it's about learning to ask better questions. So where does that leave us in a world that's both familiar and utterly mysterious, where the ordinary and the cosmic collide in unexpected ways? The next time you feel déjà vu or notice a scientific headline about some inexplicable anomaly, consider this. You might be standing at the edge of a discovery that redefines everything. The universe has never been content to fit neatly into our models, and that's what makes it worth exploring. Keep looking up, stay skeptical but open, and remember, the greatest adventures often begin with a whisper, not a bang. What we dismiss as glitches today might be the first clues to a truth far stranger than fiction, and when that truth arrives, it won't just change science. It'll change what it means to be part of this extraordinary,